What we want to do today is finish up with the famous example 90 from our CoSc book and do some demos with that. But before we do that, you had better, for the homework for tonight, my explanation of what was required in the Java program was not very clear. So what you need to do is refresh your browser, and I changed the explanation slightly to make it more clear of what I want. Basically, the homework assignment for tonight is to write a C++ program and a Java program. Now the C++ program you write using the Java Baki plugin, NetBeans plugin. And let me just say a word about that. There's two ways to use the code that I gave you. I gave you some C++ code that you could modify in a .cm file, and there's two ways you can get that set up. You could either go into NetBeans with your plugin installed and click on File, New Project, and if you click File, New Project, it will ask you for the name of the project, and you give it the name of the file that I want you to hand in, but without the .cm. And then what it will do is it will create a folder for you with a file with the .cm attached inside that folder, and it will bring up a little skeleton. It'll bring up a little skeleton C++ code, and then you could copy and paste into that. You could copy and paste the code that I gave you into that. So that's one way to do it. Another way to do it is, if you don't want to do the copy paste and do the new project, you could create your own folder with the name of the file, but without the .cm, and then put that .cm file in that folder, and then when you open NetBeans, you can open that project instead of creating a new one. I don't need to demo that, do I? Does everybody follow that okay? In fact, you probably already have. Is everybody all got that all set up? So so that's the C++ code that you need to work on. The other one, and it's a very trivial thing, it's just to add an extra process, you know, just copy paste. But it's just to make sure that our systems are all, you know, you've got it. You've got the system all set up on your computer. And then the other one is a Java program. But that one was a little less clear because in Java, I want you to put in the delay statements so that your program executes correctly roughly half the time. But I don't want the code that I gave you uses the command line arguments. Uses the command line argument to get the delay. I don't want your program to use a command line argument. So get rid of that, and I rewrote the exercise to make that clear. You should get rid of the command line argument and just hard code in the delay. I don't want to, when I test it, the test software is not going to assume that you get the delay from the command line argument. Is everybody with me on this? Are you looking at it here? Did you do the refresh? The random delay thing? Okay, let's look at that. The random delay is like this. I think what I gave you was count. Did I give you count 3? Yeah. Okay, here we can look at that. Okay, we'll go to our demo mode.
When you create a new Java project, do we...
Yes, but you know what? So the question was, when you create a Java project, do we ... and I just interrupted. Actually, what you should do, you'll never have to do that.
Okay.
I have given you, I went through and gave you
The zip.
the zip.
Okay, so you just open it.
You just open, yeah. I just uncompress that, and then when you go into Java, yeah. Okay, so here's our demo, and the question was, the delay with the Java stuff. Now, what did I give you? Did I give you count 3 for this exercise?
Yeah.
Is that what I gave you? Okay, so here's the delay stuff. The delay is this delay int 10 method, right? And we talked about this before, right? About how that delay interspersed in between temp gets in and n gets temp plus 1, how that causes the interleaving to happen, and if you don't have the delay there, the time, remember we looked at that? The time, the problem is if you don't put those delays in there, one process will probably run to completion before it ever gets timed out, and the results will probably always be correct. But see, what I did in this program, and then what you have to do is have a third process running concurrently. But what I did in this program is I did, so what you want to do is get rid of this. Get rid of this int x gets integer parse int blah, 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 and get rid of this because there's going to be no x. And then instead of putting an x here for your thing, you put an actual integer. Well, the integer that you put in here is the parameter that gets this. You're calling the constructor for count 3 here, right? And what does the constructor for count 3 do? What it does is whatever integer you give it, it sets underscore x to that value. Are you with me? And then here, whenever we do delay, it does, this delays 10 milliseconds, but then this one delays what? X milliseconds, this delay that's in between the temp gets in, between this temp gets in and the n gets temp plus 1, that delays however much you say to delay. An integer at random between
So you want us
between
to put in
1 and
actual
whatever.
numbers in the,
What I want you to do is put in actual numbers in here instead of using the command line argument.
okay.
And what you should do is fiddle around with it so that it's correct about half the time. You see what I mean? Do a little experiment. See if you can rig it up so that it's correct about half the time. And that's what I have rewritten for the, I rewrote the problem specification on the web page just today because someone came in and asked about it.
And then for this project, you can still do like clean and build and everything.
Yeah, still, yeah, you can do.
It was kind of weird. Like I clicked clean and build, and it said, "Oh, build successful."
Uh-huh.
And now I'm trying to do it again, like nothing.
Just run. I mean, after you do that, you just run it.
Oh.
In fact, running builds and runs.
Okay.
It builds if necessary and runs. If it's not necessary to build, it just runs.
Okay.
It just executes, rather. You see what I'm saying? And furthermore, look, once you do that once, oh,
I have the same here.
what happened there? I thought we had,
You gotta get rid of
I thought we,
lines 36 and 37. After you switch the extra number.
lines 36 and 37.
Yeah, if you're using hard-coded numbers instead of X.
Oh, I didn't, oh, you're right. This one doesn't have, this one expects a command line argument. Oh, that's why this error happened. Yeah. So I should run, you either need to, if you're going to use a command line argument, do you remember how to do that? What you would have to do is, we have to right click here, go to properties, and go to run, and see there's no command line argument there. So we would have to put that in order to run it successfully. But what I'm saying is you want to get rid of that anyway. So, all right, is everybody good? Okay, let's go back to our slides and check this out. So last time we looked at the try-catch finally statement, and we said the general format is, the general structure of it is try, and then you have the body of the try, and then you can have more than one catch if you want, and each catch has its own body, and then we have a finally, and it has its finally body. And we looked at this example 90 code. We looked at this method M, and remember what our author has done is very clever. We give it a 3-digit number, and that's 3-digit number, what he does with this 3-digit number is you can extract the first digit by dividing it by 100. You can extract the second digit by dividing by 10 and then modding that by 10. And you can extract the third digit by modding by 10. And he uses the first digit to control what happens in the try body, the second digit to control what happens in the catch body, and the third digit to control what happens in the finally body. Remember how we went through and we saw how that thing works? That one works. And then what he does is he's got this great documentation here, and says to exercise all paths through the try catch finally statement in method M, run this program with each of these arguments, 101, 102, 103, 201, etc. Just like this. And he gives us a little example here. Right? Now, and we did it, we ran through this with a 101 last time, and we ran through the code with 101. What I want to do now is I want to run through this with a few more. We won't take time to do the whole schmear, but let's run through it with a few more examples to see how the try and the catch and the finally works. But before we do that, let's read this. Let's read the text of this slide. This is excerpted from the book. And this says what happens if there is a finally clause. Now, this is kind of unbelievable. This is like Ripley's Believe It or Not. But believe it or not, it's true. Here's how finally works. Watch this. If there is a finally clause, the finally body will be executed. Now look, even if you think it shouldn't be executed, even if you think there's no way it can execute, it will be executed, regardless of what? Check out these regardlesses. Regardless of whether the execution of body terminated normally, regardless of whether body exited by executing a return or a break or a continue, regardless of whether any exception thrown by body was caught in a catch clause, and regardless of whether a catch clause exited by executing return or break or continue or by throwing an exception. That is an ironclad. It's ironclad. That if there is a finally clause, it will be regarded. All those regardlesses, and some of them are really are really quite unbelievable. But believe it or not, it's true. Okay. Now, so refer back to this paragraph. I think what will happen is when we do a few of these examples, we'll have to refer back to this paragraph and say, well, it doesn't seem like shit, but this was, it shouldn't execute, but it does. Okay. So let's go through. So let's go back to our demo. Now, I think what we'll do is let's keep this code, and this code for M, this code for M is what will be one of the I'll ask you a question. I'll give you this code and a 3-digit number, and you should predict what comes out. Okay, so you want to be familiar with this code. Okay, so let's go back to our demo mode. Actually, what I've done is I've set it up so that we can do this on the command line. It's much easier to do command line arguments on the command line. So look at this. Java, so I already did the CD to the package directory, example 90, and and remember what happened when we did example 90 with 101? Do you remember what it was with 101? Oh, this is kind of too bad. We're going to have to switch back and forth between this. Oh, well, I guess we can do it like this. Okay, so here's the so what was 101? Do you remember what happened with 101? The first digit wasn't 2, wasn't 3, wasn't 4. So what did it say? Try ... and then it didn't do any of those. So what did it do? It went to the finally. But now, what was the last digit? System.println finally, and then what? And then the last digit was not a 2 or a 3. So what did it do? Terminated normally with a 101, right? Okay, so is that what happens when we do this? Try finally, terminated normally with 101. Are we good? Is everybody with me? Now, I forget, last time, did we do 102? We didn't do 102? Let's try it. Let's see if we can predict 102. So, the first one, what happens? System.out.print what? Try. Now what? No, it's not 2, it's not 3, it's not 4. So what do we do? So do we catch anything? No. So then what happens? Finally, but now what happens? If A mod 10 is now it is going to be 2, right? So that's the 2 of the 102. Is everybody with me on that? It's right. Oh, I can't show it on my screen. But anyway, it's this one. So now what? But now, wait a minute. What's going to happen? It says return from finally, but then the last statement down here is return terminated normally with. What do you think is going to happen? Will it be returned? Will it say terminated normally? Okay, let's try it. So the prediction is it will not say terminated normally. So let's try it. Are you ready? Drum roll. Are we right? Return from finally. Do you see how that worked? Okay. Now, isn't this a clever example? Now let's try. What was the other one that we were supposed to try? Was there a 103? Yeah, 103. So let's try. Now let's see if we can predict 103. Now this is what you need to. You have this code. You can practice this on your own after we. Okay, so let's try to predict a 103. Try ... first, yeah, and then what? And then finally. But now what's it going to do? It's going to say throw new exception thrown by finally. And then what? That was. And then what? Will we do terminated normally? Yes or no? No, because we threw it, the exception. So now the thing of it is, so now what we have is try ... and then finally, but now here's the thing. That exception got thrown. And remember how it propagates up the call chain? Well, if it propagates up the call chain, then we don't have any more code to catch it, right? So it propagates all the way up to the main. So now you don't have to memorize or you don't have to predict exactly the wording of this. We can just say try ... and then finally, and then just say, I don't know, system error message. You see what I'm saying? So we don't have to say exception in thread main Java ... exception thrown by, you know. Is everybody with me? But we just have to indicate that that was a system error, exception error message. Okay, are we good? Okay, so now let's go back. Let's do another. Now let's do the 200 ones. So what was the next one? 201. Let's see if we can predict 201. Now what happens? System.print what? Try ... right? But now what happens? Now it says returned from try. But now here's my question. Does finally execute? Wait a minute, we're saying return, but finally always executes, even if we do a return in, okay? So when we get to the finally part, what happens? The finally body, what happens? System.print line what? Finally. So far what do we have? Try ... and then what? Finally. And now what are we doing? 201? Finally. And then terminated normally with what? 201. So what was it? Try ... finally terminated normally with 201. Let's see if that's in fact is what happens. Okay, so here it is. 201. Are we ready for this? Drum roll. Brrr. Try. Oh, wait a minute. Is this what we predicted? What happened? Try ... finally, and then returned from try. Now, how did that happen?
So does it return after the final?
So it did, so, you know, yeah, this is strange, isn't it? Because what happened normally, or sorry, we return, yeah, what happened at the very beginning? We said returned from try. So do you see that supersedes, if there were no exception thing going on, that supersedes the return terminated normally with. Do you see what I mean? I wish I could point to this on the computer screen, but I can't. Because what happened is this return executed, but then we took a bypass to the finally here. And did any of these happen? No. But we did do finally, and none of these happened, but then that return was operative. That's kind of strange, isn't it? So the finally kind of interposed itself in between that. Yeah? Does everybody see how that worked? What was that, 201?
How does it execute two returns? Well,
It doesn't. It didn't execute the two return statements. It executed that first return statement in the body of the try.
what about when we give it to
Oh, well, that's a good question. That's going to be our next one. Let's try to predict what happens if we do a 202. What do you suppose is going to happen? Because if we do a 202, what would happen? Yeah, isn't this a great demo? If we do a 202, what happens? It's going to say return from try, but then it's going to do the finally, and then it's going to say what? Return from finally. Now, we know it's not going to be terminated normally, but the question is it going to be returned from finally, or is it going to be returned, in other words, which one will take precedence? What do you think? Is that so the guess is return from finally. Yeah? Okay, so let's see if that's the case. Let's go to the terminal, and we're going to do 202. And we're guessing it's going to be what? Try ... finally, and then return from finally, right? Ta-da! It did take precedence. Now that is really This is Java precisely. Do you see what I mean? It's a really great title and really indicative of exactly what goes on. And all this is specified. All of this is specified for the behavior. Has to be specified for the behavior. All these different cases. Okay, so what was another one? What was the next one? 203. Let's try it. Let's try a 2. Okay, let's try to predict a 203. Any predictions there? Try and then what? And then it's a 2. So we do return from try, but then we take this detour into the finally body, and what happens? So try finally, and then what? Yeah, so isn't this is predictable, right? Pretty easy. Now that so what will happen? What will the output be? Tell me what the output will be. Try ... finally, and then what? Yeah, the system error message, right? Okay, let's try that. 203. Try finally, and then a system error message. Is everybody good? Was there a 204? No, 203. Next one is let's get into the 300s now. The next one is a 301. Can we predict what would happen if we enter a 301? Now what happens? System print try ... so try ... and now what? Throw new what? Exception thrown by try, and we pass the thrown by try. That's the string that gets passed, that gets concatenated with the toString of when the exception happens, right? Okay, so then, and what kind of an exception is that? That is an exception. Now, but what are we catching? Runtime exception. Do you remember the relationship between a runtime exception and an exception? It is more specific. And so a runtime exception is an exception, right? Oh, sorry. Wait. Did I say that right? Yes, a runtime exception is an exception. Is that right?
Yeah.
Yeah, that's right. Okay, so now, but is an exception a runtime exception?
Could be.
Not necessarily. So we are throwing the more general one. So do we catch it? That's the question, is do we catch it? Looks like we don't catch it, but if we don't catch it, what happens? Well, first of all, what always happens? Finally, so we do finally, but then what happens? Finally, now, what was our digit? I forgot now the number that we're talking through here. 301. We're throwing new exception. We're not throwing new runtime exception. We're throwing new exception. Are you with me? And now we're in the finally, but now what's happening? It was the 301, so none of these happen. But so now what's going to happen? We're going to get a what? Because we threw we're going to get a system error. So what should the system error come after? The try ... Yes, a system error. Okay, so let's all right, we talked through all of this, and now what were we doing? 301. And sure enough, it's try ... We predicted it correctly, didn't we? Try ... finally, and then we got the system error. Now, what was the next one? 302. Let's look at 302. We'll do just maybe one or two more. Actually, we should do a 4 to see what happens with a 4. Okay, so let's do a 302, and then we'll do a 4, and then we'll do a 400, and then we'll call it quits. So the 3. So now what will happen with the 3? So try ... This time we're going to throw. Oh, again, throw new exception. But then we don't catch the runtime exception, right? But now what happens? Finally, but now because that happens, we return from finally. But now, what do you think? Did we catch? Which takes precedence now? The return from the finally or the exception that got thrown in the body of the try? So here's the question. Will return from finally be printed out? Do you see what I'm asking? Isn't this, I tell you, isn't this something, I mean, to wrap your head around this? Because we have all these possibilities, and it's not obvious which one will take precedence. See, I mean, that's basically what we're up against here, right? Is which one will take precedence. What do you think? Let's just take a stab at it. What do you think?
Finally.
You think finally, return from finally will?
Yeah.
Because okay. Well, so you're predicting there's going to be the phrase return from finally. All right. But you think it's going to propagate up the chain and not do return from finally? Okay, so what was the number again? Remind me what the number was again. 302. Okay, so let's do a 302. Here goes a 302. Which one is it? Oh,
Finally.
return from finally. You were right in the back row. Yes.
Have some weird errors.
Yeah. Man, can you imagine? You have to, and I'll tell you, this whole exception, I have seen articles written in the computer science literature about criticizing the complexity of the try-catch finally feature in programming languages, because there are so many combinations of things that can happen, and it can be unpredictable, and it's difficult to prove correctness. You know, in other words, the complexity of this whole thing is a subject to criticism. But it's common. I mean, you need to know that it's there and how, you know, and how it works. Let's just do one more with the 400.
So is it always whichever one is last, whether it's a return or an exception?
You know, that's a good, the question is it always the one that happens last? Has it been that way so far? If it is, I have never seen that written down, and to tell you the truth, I'm not really sure myself. But terminated normally with only happens if you don't hit a return or an exception beforehand.
Exactly.
Do you-
I'm saying like then that you
Like,
But the finally, but on the other hand, if there's a 1 as the last digit of a finally, let's do a 401. Is a 401, you see, because if finally doesn't,
the 401 is
What's-
you get an exception. I was just saying like you said whatever happens. I was saying what is the
not last in the order.
not last in the order, but which one, yeah, which one is executed last? Okay. Is there a 401? Oh, 401 is not an option. What, it's 411. So let's do 411. Oops, let's go back. Let's do 411 here. Okay, here let's look through, let's trace through the code and see what we think a 411 would be. So now what happens? Thrown by, okay, try ... right? And then what? Throw new runtime exception, thrown by try. Ah, the 400s are going to be interesting, right? And now it's thrown by try. So runtime exception X. System. So now it's going to be catch, yeah. So now what? Try ... catch ... then what? But then we're going to go to what? We're always going to go to finally, but it was a 411 and a 1's not there. So now is it going to do what? It's going to do finally. No, I think, well, if you catch it,
Execution carries on.
execution carries on. Exactly. If you catch it, execution, oh, that's a good way of putting it. If you catch it, execution carries on. So then what? Return normally with what? 411. Is that right? So let's recap that. So say it again. From the top. The output will be what? Try ... catch ... finally terminate normally with 411. That's our prediction. Are we good? Here we go. Drum roll. 411. What do you think? Try, catch, finally terminate normally with 411. Are we good? So, rather than spend more class time plowing through all of these, you see how to do it. You see what, you know, okay, so we've got the concept there, and we've shown you how to do some examples. I encourage you to do it. It's a lot, see how easy it is to do on the command line? Do it on the command line, especially if you have a history. You know, you can do all these, go through in the history and just change it and boom, and you can. So maybe you get a printout, you know, and trace through the code, try to predict, and then do it and see if your prediction is right. That's a good way to learn, is like we did it, is to try to predict. Okay? Good deal. So that's our last slide on chapter 2. So now what let's do is let's go to chapter 3 and start our next step in our journey through the concurrent paradigm. Okay. Now, here's the thing, you guys. Do you realize that all the time that we've spent up until now, we have not solved a single concurrency problem? The only thing we've done is to see what the problem is. Are you with me on that? And we just did that by doing all of this interleaving stuff, you know, saw what a critical reference is, saw what limited critical reference was, saw when we could do it, consider it to be atomic. All the stuff that we've done by now, up till now, has just been, what is the problem? So guess what we're going to do in this chapter? We're going to solve it. We're going to solve the problem. But our author does this in a very interesting way. He does it, and it's really effective. It's common, and it's a really effective way to do it. What we're going to do is we're going to make several, you know, what appears to be reasonable attempts at solving the problem, and we're going to find out why each one of them fails. Because the ultimate solution to this problem, the software solution to this problem, is a little bit complex, and rather than just hitting it right away, we're going to like work our way up to it. And we're going to introduce several different ideas on the way. So, so the title of this chapter is The Critical Section Problem. Now, here's what we mean by the critical section. Now, let me give you a scenario. Let me give you a real-world scenario. Do you guys get your airline tickets online now? It's right. You can go to a website, right, and just sign up. And now, what do you do whenever you sign up for an airline? What do you do when you reserve an airline ticket online? Well, what you do is you go into the browser and you click, and it gives you all these options, and it says 2 flights left on this plane, and 2 seats left on this flight, you like that, right? And so you and your friend, you want to fly somewhere, and those 2 seats are. But then but just because you see that there's 2 flights on this one and 2 flights on the other one, what might happen when you go back to the first one and you see 2 flights, and then you actually try to make the reservation, and you take your credit card number, and then what's the last thing that happens? You click make the reservation. Then what has to happen in the system? Well, yeah, and it has to actually give you that, make the reservation for you and take your credit card number. Now look, the problem is this. What happens if someone else across town is doing the same thing at the same time you are doing it? Do you see what I mean? And what happens if you both click that button that you see, they see that there's 2, you see that there's 2 seats, you both click the button at exactly the same time, boom. Now what could happen if we haven't solved the critical section problem? What could happen? At that point, in the program, there's got to be a mechanism that does what? That sees that there's 2, and that you want it, and that it takes your card, and then you have it, and then anyone else that comes along later doesn't get it. But what would be really bad? What would be really bad is if they see you want it, and then they see the other person wants it, and then they take your credit card, and then they take the what? Their credit card, and then they give it to you, and then they give it to them, because what has happened? That's been interleaved, and there's really only 1 seat, but if that interleaving happens, they could give it to 2 people at the same time. So do you see that the critical section part is the part that has to be what? It's the part that has to be atomic. Do you see what I mean? So the 2 people try to get in at the same time, they can't. Are you with me? Now let's if you keep that scenario in mind, let's take a look at this algorithm 3.1. This algorithm 3.1 is a general format of the critical section problem. And here, in this code, you see here's the code for P and here's the code for Q, and you see that one of these lines in this loop forever is critical section. And there's the same critical section in Q. And this critical section represents that part where you want there to be no interleaving. So do you see this isn't, now why are these things looping forever? Well, the internet's running forever, and people are asking for the, they're asking for what the availability is forever. People are, you see what I'm saying? That's looping continuously. It's continuously looping. People are continually asking what's available, what's available, what's available. But finally, when what's available and they both want the same thing that's available, that's the critical section where you don't want to double book. Well, I could make a snide comment about how airlines double book these days, but but I mean, in a nice world, they wouldn't double book. So we want to avoid that. But you see how that models that situation. So look, what happens, so here's how we structure the code. The code's going to be structured like this. Inside each loop, there's going to be a non-critical section, which represents people browsing to see what's available. But then once they decide, then there is what's called this pre-protocol section. And you see, what we need to do is we need to design the pre-protocol in such a way that two people can't enter this critical section at the same time. So if P is in its critical section, Q is not in its critical section. You see what I mean? And then, after we do that, then it's okay to let someone else enter the critical section. So we have a post-protocol in each one that executes after we're done with the critical section. Now, does everybody see the general format of how that works? And for our illustrations, this critical section will be n gets temp, temp gets, what was the one that we always use for our counting? The two lines that if they interleave, it screws things up, messes things up. What did we do in the count? What is it? We had a little local variable called temp, and it was, what was it? Was it? No, it was the other. It wasn't quite. Yeah, it was like that. But what was it? No. But we wanted to add 1 to n. But we want to do it so that there's interleaving and it mimicked the load store. Wait, what was the code? What were those two lines of code? We just looked at it a few minutes ago.
It's n and it's
Yeah, I think it's temp gets n, right? And then n gets temp plus 1. And if those get interleaved, then it doesn't add it up, doesn't do all the additions right. Yeah? So that's how we will model that. So that's what will be in our critical section. And so what we want, we don't want those two statements to be interleaved. All right? Now, here comes the big concept. Any solution to the critical section problem must satisfy these three requirements. And these three, we have to be very familiar with these. These three requirements. First of all, we have to have mutual exclusion. Now, what does mutual exclusion mean? In terms of this code that we looked at over here, what does mutual exclusion mean? And what do we mean by only one can happen? In terms of this code for P and this code for Q. And the only way that can happen is if what? If P is in its what? Then what? Q cannot be in the critical section, in its critical section. Because these critical sections are going to modify this global variable. See the number of seats remaining in the plane. You see what I mean? Or n. Is everybody with me on that? Okay, so mutual exclusion means they cannot both be in their critical section at the same time. Freedom from deadlock. Now, we had you informally looked at the concept of deadlock in an assignment. What is we wrote the definition on the board. What was it? Informally, what was it? Deadlock. Or waiting for an event that will never occur, and therefore they'll be frozen. Okay, so we have to be There has to be free from deadlock, but there also has to be freedom from starvation. Now, freedom from starvation is related to. Now, what we need to do is we need to define these more precisely. Okay. Now, obviously, starvation a good or a bad thing? It's usually a bad thing. And what do you suppose starvation means in terms of this? In terms of this this scenario where we've got these things looping forever and we want to prevent them from being in their critical sections at the same time. What would it mean for Q to be starved?
Nothing, there'd be nothing for task Q.
Well, it would be wanting to do, when you're starved, you want to eat, and you can't. So if Q is starved, what do you suppose it wants to do? Well, no, not eat, but in this case, what? Get into its what? Yeah, it wants to get into its critical section, but, the scheduling happens so that it can't, so that it won't, so it starves. Yeah, that's loosely meaning that's what that is. Now what we're going to do is let's take a look at more precisely, more mathematically and more precisely what it means. So mutual exclusion means the critical section statements must not be interleaved, okay? Deadlock free, now here's where we get quantitative. Deadlock free means if some processes are trying to enter their critical sections, then one of them must eventually succeed. Now, do you see how that's a more precise description of not freezing up? If some processes are trying to enter, then one must eventually succeed. Now, you guys, here's our formal method. Here's where our formal methods really comes in handy in us understanding precisely what this means. It means there exists a P, process P, in the range what? P is trying to enter the critical section. That's a predicate, right? It's either true or false for P. It's a function that returns type Boolean. Yeah? Okay. So in the range. So in what range? There exists a P in the range. There might be 2 or 3 P's, 2 or 3 processes trying to, and for each one of those in the range, each one's trying such that what? There exists a P such that what? P actually does do what? Enters the critical section. Are you with me? So that's there exists. If some processes are trying to enter, then one must eventually succeed. Now look, what about starvation free? Here's a precise definition of starvation free. If any process tries to enter its critical section, then that process must succeed. Now do you see it's a very subtle difference, but do you see the difference? How can we write this quantitatively? If any process, it's a for all. It is. It's universal quantification, and it's a for all processes. What? Trying to enter P, they do. They all do. Is everybody? Are you with me on this? Okay. This is big concept here. Big fundamental concept in concurrent, in analyzing concurrent programs. Okay? Now, do you remember we talked about safety and liveness? And do you remember the difference between safety and liveness? Safety was what? Always something bad wouldn't happen, right? Remember the examples that we had? So now, here is the primo example of safety. So mutual exclusion, that's a safety property. Always no interleaving in the critical section. Are you with me on that? And what about deadlock free? Deadlock free, what were liveness properties? Liveness properties were things that we wanted, we wanted them to happen, right? It behaved like we wanted. So deadlock free is a liveness property. Eventually, one of several processes must enter its critical section. And furthermore, what about starvation free? It's also a what? A liveness property. So you see, eventually a particular process must enter, right? So we have one safety property and 2 liveness properties. So mutual exclusion is a safety property. Deadlock free and starvation free are both liveness properties. Is everybody, are you with me on this? On how this fits in with what we learned before in general? So this is a specific case. I want to just do one more thing because it fits right in here. Deadlock versus starvation. Now this is really cool, you guys. Deadlock versus starvation. Starvation-free is actually a stronger requirement than deadlock-free. Now, do you remember in formal methods when we did strengthening the antecedent? What does it mean for something to be strong and something to be weak in logic?
Strong is fewer arguments. Fewer.
Which one implies which one? When we say P implies, okay, let me ask you a question. If we say P implies Q, which one is stronger, P or Q? P is stronger, right? So which one implies which one? Does it say here? Starvation-free is stronger than what? Deadlock-free. Because look, isn't it true that for all P trying to enter CS, a critical section, in the range trying to enter a critical section, they enter, doesn't that imply, if it's true for all of them, then what? Then it's going to be true for one of them. Then there exists a P trying to enter V. So therefore, and you guys look at this. Here's another big drum roll. Look at this. It's from our old equation sheet. 9.20.2. As long as the range is not empty, okay, what do we know from formal methods? What do we know? For all X range R body P implies there exists X range R body P. So basically, mathematically, if you prove starvation-free, what? You've proven deadlock-free. Yeah. All right. I kept you over a few minutes. Sorry about that. See you next time.